In this unit, we've been discussing matter and how it can be classified. So first we talked about elements, compounds, and mixtures. Last class we discussed how we can describe that matter by its physical and chemical properties. So today we're going to talk about how we describe the different states it can exist in, so solid, liquid, gas. So the main ones that most people think of are the solid, liquid, and gaseous states. But there's also the plasma state. And we're going to talk about how we describe the properties of each of these four states of matter. So in the solid state, substances are going to be densely packed. So you can look at this molecule here. This would be like representing what its atoms would look like. So very densely, tightly packed close together. So they have an exact shape, they have an exact volume, and we cannot compress them. So you can't compress them into a smaller volume. So they do not take the shape of their container, they maintain their shape, they're going to maintain their volume, and they cannot be compressed. So examples can be in diamonds or salt, any one of those. And there's a lot more. So liquids are going to be tightly packed, but they're going to be far enough so that they can slide over one another. So they're not as tightly packed as solids. So here you can see a picture. So the molecules are a little bit more loose, so they kind of flow. So they have an exact volume, so we can measure this, maybe like 10 milliliters. But they don't have an exact shape. So whatever container you put them in, liquids are going to change their shape. And again, we can't really compress liquids. So some examples could be like mercury, which is a liquid, or bromine, which is an orangish liquid. Our third state of matter are gases. So gases are far enough apart, are very far apart, and they move very freely. So here you can see a picture of what they look like at the molecular level. So they do not have an exact shape. They're going to take the shape of whatever container they're in. They don't have an exact volume. They're going to, again, take the volume of whatever shape they're in. But you can easily compress them. So we could compress this down into a lot smaller volume. So examples, so here's bromine, but it's in its gaseous state. Or chlorine, which we talked about at the beginning of this unit, also a gas, like a yellowish tint to it. So what happens if we were to raise the temperature to super high levels? So somewhere between 1,000 degrees Celsius and a billion degrees Celsius. Will everything be just a gas? What do we think? So the answer is we're going to get a plasma. So plasma is going one step further than a gas. So we're going to heat it up so it's so hot that it separates into something called an ion. So a charged particle. So if we're thinking about like water, and we ionize it, it's going to turn into hydrogen and an OH ion. So plasmas are very good conductors of electricity. So where do we see plasmas? So in flames, where it gets really hot. Lightning usually ionizes some of the air around it. The aurora borealis, or the aurora australis, so the northern lights. So those are charged particles that are coming into our atmosphere. They become ionized gases. The sun is a plasma state. Or any star for that matter is in its plasma state. So plasma is actually the most common state of matter in the universe. Okay, not on Earth, but in the universe. So all of the stars are made of plasma. So how do we change between our between our phases? How do we go from a solid to a liquid, or liquid to a gas, and vice versa? So we have to go through something called a phase change. So when you add energy or you remove energy, you can change from one phase to another. So you can go from a liquid to a solid if you remove some heat, or you can go from a solid to a liquid if you add heat. So heat is that thing we're transferring. So heat is just another word for energy. So it's a transfer of energy from an object at a high temperature to an object at a lower temperature. So heat always flows from hot to cold. So let's describe our phase changes here. So to go from a solid to a liquid, we call that melting. You're very familiar with that. Going from a liquid to a solid, we call that freezing. Going from a liquid to a gas is vaporization. Going from a gas to a liquid is condensation. Right, on a hot summer day, you have your glass of soda sitting outside with ice in it, and you see it gets wet on the outside, so that's condensation, so moisture from the air, condensing or cooling down because it comes into contact with your cold glass, and it condenses into a liquid. Some of the more unfamiliar ones, sublimation, going from a solid to a gas. So that occurs in dry ice, so thus the name dry. So it doesn't go to the liquid state. It goes directly from solid, dry ice, carbon dioxide, into the gas form of CO2. We can also go in reverse. So going in reverse, we call that deposition, depositing like a solid. And then another more unfamiliar one is turning into a plasma. So going into a plasma, we call that ionization, and in reverse is deionization. But again, we're going to focus mainly on the solid, liquid, gas. We don't deal with a lot of plasma. So some of these phase changes are going to need to add heat, and some of them we need to remove heat. So phase changes where we add heat, we call those endothermic, like heat is entering. So we have to add heat to melt something, to vaporize something, or to cause something to sublime or go through sublimation. Changes that need to remove heat, we call those exothermic. So freezing, condensation, deposition, you all have to remove the heat to cool down and cause its temperature to drop and change phase. So exothermic, like exiting. So to represent these phase changes, there are two ways we can cause that phase change. So the most common thing most people think of is changing temperature. But we can also change pressure and change phases as well. So we use a phase diagram or a graph that's going to show us when a substance exists as a solid, when it exists as a liquid, and when it exists at a gas. So what temperature and pressures does that occur at? So that's called a phase diagram. So for example, here's what a normal one would look like. So let's describe the regions. So you want to label your picture as well. So our x-axis is always going to be temperature, down here, usually degrees Celsius. Pressure is going to be our y-axis, usually in something called an ATM, which stands for atmospheres, a unit of pressure. And then we have our three regions. So this first region is always going to be your solid region. The middle region here is your liquid, and your gaseous region is over here, towards the bottom and towards the right. There's also a point where all three lines meet. So this line here between the solid and liquid would be either melting or freezing. So if you're going from here to here, you'd be melting. If you go from liquid to solid, you'd be freezing. This line between the liquid and gas, you're either vaporizing, if you're going from liquid to gas, and if you go in reverse from gas to liquid, you would be condensing. This line here, between the solid and gas, you go from solid to gas, you're subliming. If you go from gas to solid, you're going through deposition. So this point in the middle here, where all three of these lines come together, is called the triple point. So it represents the temperature and pressure where all three phases coexist. And this really happens. You can get a solid, liquid, and a gas all at the same time. So you're boiling and freezing at the same time, or you're melting and subliming at the same time. So that point does exist. If you're interested, look up some YouTube videos on the triple point, and there's a lot of them out there. So a point where all three phases, so solid, liquid, and gas, exist all at the same time. The other point is the point out here. So we call it the critical point. So anything past, so I'm going to kind of use my mouse to draw a line, anything past this point is something called a supercritical fluid. So it has some unique properties that are not like a liquid and not like a gas. So it occurs normally at extremely high temperatures and pressures. And we say that the gas and liquid phases become indistinguishable. So we're not really sure how they're going to behave. So that's what we call a supercritical fluid. So those are the main points on our graph. So let's practice reading them. Oh, I forgot one thing. So we have something called the normal melting and normal boiling. So this is where it would normally melt and normally boil. And we measure that at sea level. And sea level occurs at 1 atmosphere. So if there's a question on your homework that asks what is the normal melting, you would find 1 atm. You would go across to where it would melt. Remember, melting occurs between solid and liquid, so we're going to this line. So we would go down here and we could read our melting point off the bottom. Same thing for normal boiling. It's going to occur at 1 atm. We go across to the line between liquid and gas where it boils, and we would go down and read the temperature to get our boiling point. Okay, so let's practice reading this one. So what is the temperature? What is the critical temperature? So that's going to be our critical point. Remember, that's the point between liquid and gas at the very end. So our critical temperature would be somewhere between 700 and 800. So I would say 750 degrees Celsius. Okay, question 2. At what temperature and pressure would the 3 phases coexist? So 3 phases, that has to be our triple point. Remember, our triple point is where the 3 lines come together. So our pressure would be 50 atms, and our temperature, we'd go down and read it off the scale, would be about 350 degrees Celsius. Okay, if I had a bottle of compound X at a pressure of 45, so let's find 45, so somewhere here, and at a temperature of 100, so my point is here, what would happen if I raise the temperature to 400? So if I go from 100 to 400, I cross the line between solid and gas. So that would mean I would sublime. Solid to gas is sublimation. And the last question, if I wanted to, could I drink compound X? So if I were to drink it, it would need to be in a liquid phase, so somewhere here. Remember, water boils at 100, way down here. So when it's in its liquid phase, it's somewhere between 300 to 750 degrees Celsius. So there'd be no way you would want to drink this liquid. It would be way too hot. So the answer to that question would be no. So you're going to practice a little bit more on your homework for today.